Thank you, the organizers, for allowing me to speak today. My presentation is about cosmology from galaxy redshift surveys, presenting the current results and future prospects. So let me start by reviewing two of the main observational probes in cosmology, the CMB and the large-scale structure. So large-scale structure has potentially much more information than the CMB because it's essentially a three-dimensional volume opposite to the CMB, which is a two-dimensional surface. And also large-scale structure happens at later times when dark energy is the dominant source of energy in the universe. However, there are several drawbacks that we have to overcome in order to use large-scale structure as a source of cosmological information. And these are, for example, we need to understand galaxy formation bias at some point. We need to account for having velocities of peculiar velocities of the galaxies, as well as having gravity very strong presence in later universe, opposite to what happens at early times. So essentially, we get information from large-scale structure observing, so through spectroscopic surveys, which observe essentially two things. It observed angles and it observed redshifts, angles and redshifts. And redshifts are converted to comoving distances, assuming essentially two things. We need to assume a cosmological model, and also we need to assume that the recession, that the velocity associated to the redshift of the objects are entirely due to Hubble recession velocities. And we will see how these two assumptions enter into play when we need to extract cosmological information. So this is the outline of my talk, how to, from these large-scale structure maps, how we compress these into what they are called summary statistics, how we identify robust features into these summary statistics, namely speaking the BEO and redshift space distortions, and how these are interpreted under the umbrella of a certain cosmological model and extract information on dark energy, gravity, or if we want inflation as well. So let's start with the summary statistic compression. So these galaxy maps are essentially non-deterministic objects, but they have like statistical properties that they can be described through endpoint correlation functions. So what we do is to compute a series of endpoint correlation functions from these maps, which they are going to tell us the statistical properties. So strictly speaking, these maps are essentially non-Gaussian fields for galaxies, which means that it's not only, so the two-point correlation functions or the Fourier space counterpart, the power spectrum, do not contain the full information, but there is extra information in the three-point correlation function and the four-point correlation function. So for those which are not familiar with these functions, two-point correlation function essentially is counting pairs of galaxies at certain distances. Three-point correlation functions is counting triplets of galaxies, and so on. And the Fourier counterpart, the power spectrum, bispectrum, and trispectrum, are just mathematical artifacts, but the physics behind it is the same. So in this talk, I'm just going to focus on the results on the two-point statistics. But for instance, for reference, there have been other studies using three-point statistics using observational data, which I leave you here. So one of the features that we want to identify in these functions is the BEO. So for those who are not familiar with BEO, this is generated in the early time universe when the universe is a plasma with coupled photons and baryons, and there are some oscillations which produces sound wave which travels through this plasma during a certain time until recombination when the plasma disappears. And essentially the time that this pressure wavelength have been traveling is it's what is called sound horizon scale. And it's getting printed not only in the distribution of photons at recombination time, but also at later times in the distribution of matter and essentially in the distribution of galaxies. So by identifying this feature in the distribution of galaxies, then we can do cosmology. And essentially we can trace the expansion history along the universe if we know which is the absolute size of this recombination scale, which is usually called as calibrated BEO analysis, but also even without knowing which is the absolute size of this sound horizon scale, we can do cosmology through what is called uncalibrated BEO. And I'm just going to describe briefly how this is done. And how this is done is done through what it's called the Alco-Paczynski. So one of the main assumptions that we are going to do that we assume when we do modern cosmology is the cosmological principle, which says that the universe is isotropic and homogeneous. And essentially, by measuring departures from isotropy, then we can know things, cosmological information. So when we convert redshift into distances, we, as I've said before, we need to assume a model, and this model is usually referred to as fiducial cosmology or reference cosmology. And if this cosmology is slightly different from the actual cosmology, we are going to introduce some source of anisotropy. By measuring this source of anisotropy, then we are going to know how far away we are from the actual cosmology. And this affects all the scales, but in particular affects BO scale, which is a scale we can measure very well. And this allows us to measure the BO along the line of sight, which is proportional to the Hubble function at that redshift, or the inverse of the Hubble function at that redshift, that we are going to refer to as dH. But we can also measure the BO across the line of sight. And this is going to be the integrated, it's essentially not the Hubble function, but the Hubble function integrated from 0 up to a certain redshift that we observed, and this is going to be called dm, or angular diameter distance. So using these two BO measurements along and across the line of sight, we can do cosmology. As I said before, the absolute size of the BO is set at recombination time by this sun horizon scale, also referred to as RD, but we don't measure this because galaxies surveys are tracing dark matter at later times. So at later times, we still identify some BO, and that absolute scale of this BO, it's this horizon scale RD, whatever it is, times the Hubble expansion up to that time. So if we have information on RD from other sources, then we can infer the expansion. However, even if we don't know RD, by actually comparing the size of the BO along and across the line of sight, the relative size, which is called, which is the actual Alkop-Paczynski test, or uncalibrated BO, then we can get information on cosmological parameters, namely omega mater, and if we don't assume flatness, also omega lambda. From the isotropic dilation, so the absolute scale of BO, if we get information on RD, then we can infer H0, but if not, then we will constrain this magnitude. So essentially, the takeaway message is from BO, we can get essentially these two things. There is another source of anisotropy, which are like the redshift space distortions. And again, we assume that the universe is isotropic and homogeneous, and departures from this isotropy, they can be quantified as redshift space distortions. So this happens because the redshift we observed, we associate it to the Hubble flow, the radial velocity distance due to the expansion, but it is not totally true because we know that galaxies attract each other, and therefore they're going to have an additional component of velocity due to these peculiar motions. And these peculiar motions are actually parameterized through this F parameter, which is called logarithmic growth of a structure, which essentially depends on two things. Depends on the amount of matter in the universe. So the more matter we have, the more strongly galaxies attract to each other. And also the theory of gravity, of course, which usually it's parameterized through gamma. How this looks into visually, this is how the true real space isotropic field would look like, and the redshift space distortions are creating some distortions along the line of sight. So we see that if the observer is here, the line of sight are these imaginary lines we can draw from our observations, and we see that there is some anisotropy that essentially at large scales it produces a squashing of structures along across the line of sight. So in order to get a bit more insight on what redshift space distortion does, we can play with this Kaiser toy model. In reality, we don't apply Kaiser toy model, we apply a more complex model, but I think in order to get the general idea, it's useful. So our galaxy power spectrum relates according to Kaiser toy model with the matter power spectrum through galaxy bias and this other stuff. So if we are observing galaxies across the line of sight, the angle between the two pairs of galaxies and the line of sight is 90 degrees. Beta, in that case, would be 90 degrees, cosine of beta 0, mu 0, and we get exactly the real space prediction, which is matter times bias square is the galaxy velocity. If we observe pairs of galaxies which are not totally across the line of sight, but it has a component of velocity, which is proportional to this cosinus of beta, then we will have this arising component of which would enhance the power times this growth of structure. Instead of working with these two variables, k and mu, then we can also expand these in terms of Lagrangian base, and the amplitude of the first Lagrangian moment is what it's called a monopole, quadrupole, and an hexadecapole for the other. So this forms what is called the isotropic signal, and this forms the anisotropic signal. Doing some basic operations, we can relate this monopole, quadrupole, and hexadecapole with the matter power spectrum and with these amplitudes, which depend essentially on two things. It depends on the bias and it depends on F. Using only one of these multiples, both are degenerate, but at least using two, we can break the degeneracies between F and B. It's also have to remember that the amplitude of the matter power spectrum is unknown. So this is usually parameterized as sigma 8. So what we measure is not F, but F times sigma 8. So coming back to the original picture from galaxy maps, we have seen how compressing this into summary statistics, namely speaking the correlation function or the power spectrum, we have identified some features, the BEO and RSD, and we have essentially compressed per redshift bin these in three quantities, the BEO along the line of sight, the H, the BEO across the line of sight, the M, and F sigma 8. So just to remember, these two quantities depend on the background expansion, whereas this third quantity, F sigma 8, depends on perturbation level. And now we are going to see how this will get interpreted in terms of cosmological parameters. But before going to this, let me review what BOSS and eBOSS surveys are. These are spectroscopic surveys. They have been observing several sets of galaxies in the northern hemisphere, but also a part in the southern hemisphere. Galactic hemisphere, of course. And this corresponds to different traces of dark matter, and by identifying different traces, what we are actually looking is at different distances. So from nearby galaxies around redshift less than 0.2 to LRGs, which are luminous red galaxies and intermediate redshifts. And if we go even to higher redshift, we see these emission light galaxies, which are young blue galaxies with a lot of star formation. And even at higher redshift, we see quasars, and even at higher redshift, we see this Lyman alpha, which is neutral hydrogen, which get ionized by the light of quasars in the background, which allow us to trace dark matter at very large scale. So overall, we will have more than 2 million spectra tracing this redshift. So these are the number of eBOSS, but of course, eBOSS, it's not only its numbers, it's a lot of people, it's a huge effort within the collaboration. We've been meeting in one or twice per year since particular I joined BOSS in 2013. It was like the beginning of BOSS. And along this year, all these people have been putting a lot of effort in order to extract very carefully the information from these catalogs, convert it into Redshift, accounting for systematic errors in order to make a final catalogs which are reliable and trustable for cosmology. So this is like the final picture that eBOSS tell us. Again, this part here is the northern galactic hemisphere observations. This is the southern galactic hemisphere observations. These gaps here are obscure regions by our own galaxy, and the different colors are just tracing different dark matter traces, again, from nearby galaxies in green towards LRGs in magenta and red, emission line galaxies in blue, quasars in yellow, and finally, this Lyman alpha hydrogen clouds in white. So there is an animation. If you access to the slides and you click here, you will see an animation of these pictures, which I'm not going to play because of time reasons. So last year, in the 17th of July, we're coordinating the final release of the whole BOSS and eBOSS papers. There were like a coordinated submission of around 20 papers, so that was a lot of effort, not only in terms of cosmology interpretation, but also in how the catalogs were built, and several BEO and RSD analysis in terms of in configuration space or in Fourier space on the different samples from LRG to ELGs, quasars, and Lyman alpha. Not only that, but also how the synthetic catalogs, which are called galaxy mocks, were produced, that they allow us to put reliable error bars on our measurements, as well as some mock challenges we did in order to account for systematic budget related to our theoretical models, as well as other studies which are beyond the standard, the state-of-the-art analysis. So just as a summary of what eBOS and BOS is producing, we have separated the whole 3D maps in Redshift beams. For each Redshift beam, we have measured the power spectrum multiples, monopole in blue, quadrupole in red, and hexadecapole in gray. And from each of these samples, we have identified these two BO distances and F sigma 8. And now I'm just going to talk about which are the interpretation in terms of cosmological model. So the first thing is, what can BOS and eBOS tell us about dark energy? So we knew dark energy existed from Planck and supernovae, but now we have a third proof of dark energy, which is represented in blue, which is the uncalibrated BAO. So the uncalibrated BAO alone can rule out a dark energy equal 0 by many sigmas. And how is that the BAO can do this now? So the unfair advantage of BAO is that it's using BAO at different redshifts. So by combining this measurement of BAO scales at different redshift, from redshift almost 0 to redshift 3.5 from the Lyman alpha, we can break a lot of degeneracies and finally getting such a neat and nice constraint on omega lambda. So another thing that BAO can tell us very well is that the universe is very close to be flat, which is represented here by this line. And it happens to be that the three proofs of dark energy, supernovae, CMB, and BAO, they all more or less cross in a region where the universe is actually flat. So another thing is what happens with more exotic models of dark energy. So this is usually parameterized as this time evolving dark energy equation of state with two free variables, W0 and WA. And here we allow as well to a non-flat universe through this omega k. So we see so blue here is SDSS BAO combined with Planck, and red is supernova combined with Planck. So supernova, I mean uncalibrated supernova, of course. And we see here that, for instance, BAO is very good, as we have said, in constraining these flatness parameters we see here, but not very good at constraining W. It has a very wide posterior. However, when we combine these proofs from supernovae and BAO, then we can break these degeneracies and we obtain something which is the gray contours, which is very close to the actual lambda CDM model with its flat universe without time evolving dark energy. So Vivian has talked before lunch on this problem in modern cosmology, which is the Hubble tension, H0. And so what BAO can tell us about this? So as I've said before, BAO alone cannot constrain H0. It constrains H0 times RD, the sun horizon scale, which is represented here in this blue band. But however, we can combine the BAO with something which is called BBM, which essentially is a measurement of omega baryon, and assuming that we know that there is no early dark energy and there is no exotic fluid in the early time universe, then we can compute RD. And this is shown in these dark blue contours here. So, BAO calibrated with BBN, calibrating the sun horizon scale with BBN, without using any CMB experiment. It tells us that the H0 is around 67. Here is represented by the Planck results in CMB in gray, so there is a very neat agreement. We can do also what is called the inverse distance ladder, which is combining CMB with BAO, in this case calibrating BAO with CMB and adding as well the uncalibrated supernova, so the unanchored supernova. And you see here that even allowing for the full freedom in the model, so like a non-flat universe with time evolving dark energy, we get like an H0 value, which is very, very consistent with what Planck wants. So just to, as a curiosity, we can also take the BAO, and instead of calibrating the BAO with BBN, what we can do is to use the distance ladder measurements to calibrate H0 and then see which is the horizon scale that we would expect in order to have the correct anchor distance ladder combined with BEO. And this is shown in this plot. So we would need a sound horizon scale of around 135. So this is like, well, we talk about H0 tension, but actually we could be talking about sound horizon scale tension. Just to finalize, let me just talk about as well as neutrinos. Cosmology is sensitive to the total sum of the mass of the neutrinos, and there is a slight preference for the normal hierarchy. So just to remind you, there are two hierarchy depending on whether we have two massive neutrinos or one massive neutrinos, and this predicts essentially two limits for the total mass of neutrinos, which is 100 MeV or around 660 MeVs, which are represented here by these two regions. So Planck alone cannot constrain this very well, but when we add the BEO to the Planck measurements, and even when we add RSD and BEO to the Planck measurements, then this is represented as the solid lines, that they are the posteriors, that they are drawn from this hard prior, the physical hard prior, saying that the sum of the mass of the neutrinos has to be at least 0. So obviously we are not seeing any maximum, because if we take these posteriors and we fit a Gaussian fit to those, then we see that the theoretical maximum of this posterior is lying into this unphysical region of negative masses, which has no physical sense. So this is just to illustrate that when we interpret this posterior as 1 sigma or 2 sigma tensions, then we have to bear in mind that under the Gaussian interpretation of the posterior, this posterior is having a maximum in a non-physical region. So right now, as I've said, there is a slight preference for the normal hierarchy of the neutrinos according to cosmology, but there's still not enough data to say that this is really strong. So this was for the stage 3 experiments, and I think the POS and EBOS is one of the, if not the last, spectroscopic stage 3 experiments, and now we have started with the stage 4, and the first stage 4 spectroscopic instrument that is working is the dark energy spectroscopic survey. It has started already observations this year, a few months ago, and it will last in principle until 2026. So it will collect a lot of data. We'll cover 1/3 of the sky, 14,000 square degrees, and as POS and EBOS will cover this redshift range from 0 to 3.5, covering observing different dark matter traces from nearby galaxies in this so-called bright galaxy sample, LRGs, emission light galaxies, quasars, and Lyman alpha. So there is an expected release of results by the end of next year that it will correspond to the first year observation, that roughly speaking, it's around 1/5 of the area. And here I'm just showing some forecast for what DESI will deliver in black lines. In this case, I'm showing just the BEO, the isotropic BEO distance scale error. So in blue and in green, there are the POS and EBOS results, which are around few percent measurements in terms of error, and we will see how DESI will reduce these error bars down to sub-percent measurements. Not only BEO, but as for POS and EBOS, DESI will do redshift space distortions, and we expect that it will put very strong constraints on this growth of the structure that it can detect if happens deviations from the predictions of gravity. So in my last slide, I'm just put the summary here that these are the state-of-the-art results of the stage 3 experiments in terms of spectroscopy. We have observed over 2 million spectra. We have sampled BEO distance scales from redshift 0 up to redshift 3.5, and in terms of growth measurements up to redshift 1.5. In general, I would say that there is a good agreement with lambda CDM and Planck results. BEO itself, it consists on a detection of dark energy. Now we have 3 independent proofs of dark energy, so this is really something very strong, and it cannot be caused by some uncorrected systematics. But not only that, BEO is very good at proving flatness, especially because it has this redshift dependence on the BEO from redshift 0 to high redshift. And the near future, it's DESI, which has started already observing, and stay tuned because by the end of next year, it will produce, I'm sure, some amazing results. And that's it. Thank you.